two semicircles are placed in a circle as shown in the figure below. Find the area of the shaded region with respect to area of the circle. Okay. First thought, this is a beautiful shape, and there's a semicircle here and semicircle here. First of all, I thought of this and said, look, this doesn't look like anything is given in this question. No data is given. And so how are we going to compare? They have not told us where the larger semicircle is positioned, where the smaller semicircle is positioned. But the key takeaway here, if the larger semicircle becomes bigger, the smaller one becomes smaller. The semicircles are placed in such a way that if you keep growing this, that will become smaller. If you keep shrinking this, that will become bigger. Right? Which tells us that there is some relative basis for this. That we can still answer the question without knowing exactly where this is positioned. Now, the moment we discover that, and hopefully the choices don't have a cannot be determined and all that, then you can always do a fudge. My preferred fudge is very straightforward. So put a circle. The first fudge we can think of is make these two semicircles equal. So pass through the center. Pass through the center. Two equal semicircles, find that, and we are true. The other fudge, which is even better, yes, it is telling us no matter where the semicircles are, you make one bigger and bigger, the other smaller and smaller. Wherever you go, the answer doesn't change. We've tried to make both equal. Let's go to the other extreme. Let's say we keep making this bigger and bigger and bigger, and this smaller and smaller and smaller, to the point where finally this vanishes and only this remains. What will we have? We'll have a beautiful semicircle and nothing here. And then therefore we know with respect to the area of the circle, the shaded portion is 1/2. Now we'll have to probably prove that this is also 1/2. We'll have to prove this is 1/2. But we are mathematicians. We're not trying to answer a multiple choice question and celebrate pi day. What's the thrill in that? And so we're going to say, how do we now prove that wherever this is, the area ratio is constant, and then therefore we can compute it, which will turn out to be 1/2. I'm reasonably confident. But then proving that irrespective of the size of the larger or the smaller semicircle, as long as this condition is met, the two semicircles, as long as that idea is met, you're through. Let's try to do that. And how do we do that? Let's try this. And I'm going to mark out the center of the circle, of the larger circle. So this is radius, this is radius. We can do that. Right? Now I'm going to say radius of this semicircle, let it be R1, or this one, let it be R2. Right? From this meeting point, if you draw this line, the two semicircles are tangent to each other at this point, which is clear. This is R2, this is R1. Right? Now, if you imagine this circle, then you say, I can draw this line and this line, or from the center, I can draw this radius, center of the larger circle. Okay. Now think about this. Think about writing an equation for R using R2 and R1, and then imagine a scenario where we increase R1 and therefore reducing R2, etc., etc., etc. Okay. To start with, this distance is R1 plus R2. We know that, right? Now R, there is a small delta here. If you take this triangle, then you can say R square is R2 square plus this square. And let's say we name this, we call this as O, this is P, this is Q, this is R. Then R square is R2 square plus OQ square. R square is R1 square plus OR square. Now, if we find OQ square, OR square in some form, we are through. What do we know? We know OQ plus OR is QR, which is R1 plus R2. Right? OQ plus OR is R1 plus R2. I'm going to do this algebraically, but before that, let's think about this. We have this plus this being R1 plus R2. R1 square plus one part of its square is R square. R2 square plus one part of its square is R square. Think about this. This is R1 plus R2 overall. There's an R2 sitting here and R1 sitting here. These two should be equal. Radius square should be equal. Right? So if you reframe this equation, R2 square minus R1 square is OR square minus OQ square. And so just imagine this. I don't want to do this algebraically. R2 square plus OQ square is R1 square plus OR square. These two are equal. OQ plus OR is R1 plus R2. Think about this. Where will it work? These two add up to R1 and R2. There's an R2 here, there's an R1 here. If this were R1 square, this were R2 square, this will work like a charm. This will be R1 square plus R2 square, R1 square plus R2 square. Or if this part were R1 and this remaining were R2, we are through. You can straight away see if it were not the case, then we won't be through. It won't work. Or that is the only solution. Or R1 square plus R2 square is R square. The moment you have it, you're through. How are we through? Think about this. An area. This is pi R1 square by 2. Pi R2 square by 2. This is pi R1 square by 2. Add these two. We'll have pi by 2 into R1 square plus R2 square. Just pi by 2 into R square, or the shaded regions amount to half the area of the oblong circle. Right? The algebraic proof, right, where you're saying R2 square plus OQ square, I'm going to write it down here, R2 square plus OQ square equals R1 square plus OR square. So R1 square, sorry, this is R2 square. R1 square minus R2 square is OR square minus OQ square. Try that out. You should get the answer. I'm just going to leave the framework here. So let's think about this. I'm going to R1 square minus R2 square. So I'm going to write it down here. R1 square minus R2 square equals OR square minus OQ square. OR plus OQ is R1 plus R2. Call one of those as X, the other as R1 plus R2 minus X. Solve. You'll get X is the corresponding opposite one. So the two triangles quite beautifully have sides R2 and R1 and R1 and R2. Right? Adding R1 square plus R2 square is R square, which is what gives us that this semicircle area or this semicircle area is half the area of the circle. Hush.